Good afternoon, everyone. I want to welcome you to my lecture today. Of course, today the focus is going to be on some common unbiased estimators. You remember earlier in the week, I introduced you to, bias and mean-square error. We started a new chapter that I call Chapter 8. Of course, today we're going to focus more on some common unbiased estimator that we use in statistical analysis. So in the outline, I'm actually going to walk you through point estimators. I remember I told you the other time we got two types of estimator, point and interval. So before going to interval estimator, we need to first understand, we need to first, put forward what we call point estimator. So today, the common estimator we're going to be working on is going to be sample mean, okay? So sample proportion, difference of means, and difference of proportions. So these are common estimators, okay, that we use. And you know what? You're actually going to see reason why we use them in statistical analysis, okay, because they are unbiased. That's why we use them. We prefer estimator that are unbiased. Not only just unbiased, they also have minimum variance. And that doesn't mean bias estimator is bad. That doesn't mean it's bad. Okay? Okay. I think I'll four of us walk you through again the definition of unbiased estimator, what makes an estimator to be biased and what makes an estimator to be unbiased. Unbiased estimator, what makes an estimator to be biased and what makes an estimator to be unbiased. I gave you the other time this definition. Okay. Now we have the idea actually start from situation where we want to figure out the true value of a parameter. And of course, we are limited by budget. We can't study every element in the target population. We're going to work with sample, right? Working with sample, we need a method. That method is what we call an estimator. Now, estimator here is a theta cap, denoted as theta cap. So it's actually going to be called a point estimator for a parameter theta. And we're going to say a theta cap, which is an estimator, is unbiased when the expected value of theta cap is the same thing as the true value of the parameter. So which means, don't forget, theta cap is a random variable, right? The mean of theta cap will actually give us the true value of parameter. When that happens, that is what we call unbiased. Okay, that estimator is unbiased. And on the other hand, it is biased when the expected value of the estimator is not the same as the true value of parameter. Okay. And if you want to determine the bias, okay, if I want to determine the bias, I only need to compute this guy here. The bias of a point estimator is mathematically denoted as B into estimator equal expected value of the estimator minus theta. That is a formula that I'm actually going to use if I want to investigate whether an estimator is biased or unbiased. When this formula gives 0, when the bias of an estimator equal to 0, then the estimator is unbiased. But when it is not equal to 0, not equal to 0 means it could be negative or positive, then it is said to be biased. Does that make sense? Okay. I want to move right now. You remember I promised in my last lecture that I was actually going to talk about the mean square error. Actually, extract this from the last material that we did on Monday. Now, take it. Let me tell you this. When we have an estimator theta cap, okay, if it is unbiased, how do we evaluate? Okay, how do we evaluate whether an unbiased estimator is good? We're going to make use of variance. Okay, what about bias estimator? What do we use for bias estimator? If I want to evaluate the goodness, if I want to evaluate the reliability of a bias estimator, then I'm actually going to use mean square error. Now, what I want to walk you through now, what do we mean by, what is the difference between mean square error and variance? I need you to listen now. What is the difference between mean square error and the variance? The variance, we actually measure a distance between an estimator and the mean of the estimator. The distance, okay, the square distance, okay, the square distance between an estimator and its mean. That is what we call variance, okay? But what about mean square error in the actual sense? The mean square error also measure the mean of the square of the distance, but this time around between an estimator and the true value of a parameter. The distance, the square, okay, of the distance between an estimator and the true value, that is theta of a parameter. You can see the difference between the two. But let me tell you this. The mean square error is a combination of the variance and the square of bias. And that is what we want to prove right now. We want to prove this guy. Take a look at that guy. We actually want to prove that the mean square error of a bias estimator, because we use mean square error for bias estimator. So the mean square error of an estimator can be written as the variance of the estimator plus the square of the bias. When the bias of an estimator is 0, what happened? When this guy equal to 0, then that estimator become unbiased, and it's actually going to have the expression for the mean square error and the variance, they will be the same. Does that make sense? Which means if I have an unbiased estimator, the variance of an unbiased estimator is the same thing as the mean square error of an unbiased estimator, because the bias equal to 0. Now, I now want to prove this. I want to prove how the mean square error of an estimator can be broken down into variance of an estimator and the square of bias. And I need you to focus the board. I'm going to start with this. Let expected value of theta equal to C, or of theta cap equal to C. Okay? You remember when we have an expected, when we have a theta cap is a random variable, we can find the mean. The mean of a theta cap is the expected value of the theta cap. We are now denoting that as C, like, oh, we're getting a value. Does that make sense? Now, look at the definition of a mean square error. I told you the other time. The definition of a mean square error, we're actually talking about, the mean of the square difference between the square distance between estimator and the true value of a parameter. You can see right here, right? Estimator, theta cap, minus theta. Estimator is a point that is theta cap is the estimator, and theta is the true value of the parameter. Don't forget what we do in the law of large number is when the sample size is sufficiently large, we expect an estimator to converge to the parameter. You remember we did that, right? When we said the sample mean converges to population mean within a certain distance. Let me also tell you this: the law of large number provide a foundation for central limit theorem. The law of large number, in other words, facilitates central limit theorem. And let me tell you this: an estimator may be biased, But when sample size is large, it may be unbiased in the process. And what do we call that kind of unbiased? Initially, it was biased at small sample, but when sample size is large, it became unbiased. That is what we call asymptotic unbiased. Do you know the meaning of asymptotic? Means large. But on the long run, when sample size is large, then it becomes unbiased. But that is not where I'm going. If you take a look at the formula for the mean square error now, if I now introduce mathematically, I introduce C and negative C, it's still the same. Because negative C will cancel positive C, right? That I introduced. Now, I now group that. When I group that now, that will enable me to use a law in mathematics. Oh my God. You see the reason why we do algebra in high school. A plus. Now, if I have A plus B or squared, that's going to give you A squared, B squared plus 2AB. Okay, if you take a look at what you see now, theta cap minus C is A. C minus theta is B. Now, if you apply the rule there, you're actually going to have this guy. That's why you have that guy. Okay? So foundation of statistical theory is mathematics. You need the knowledge of algebra. Okay, now, if you take a look at that now, then I want to use expectation to multiply all of that. Okay? Now, I'm going to have this guy. I'm going to have this guy. Okay? Then I'm going to... So, at the end of the day, I'm actually going to find myself here using expectation to multiply all of that. Okay? I'm actually going to... Now, if you take a look at this side, expectation disappeared. Here, expected value of theta cap we've been given to be C. Did you see how it disappeared? This now becomes C minus C. And what happened to what you have in the middle? It's actually 0. Do you see that now? Now, we are now left with this guy and this guy. Now, when you take a look at this guy, when you take a look at where we are now, when you take a look at this guy, what is the expected value of theta cap minus theta? That's a bias of an estimator. Okay, what you have there is a bias of an estimator. Then we're going to we're squaring the bias of an estimator. That led us here. And what is a random variable minus? It means squared, and you take in expectation. Like for instance, you have expected value of y minus y bar squared. That is the variance. That is the variance. So that is why this guy is the variance here. This guy is the square of the bias. And this is how we prove that the mean square error of an estimator is actually partitioned into the variance of an estimator plus the square of the bias. Now, because of that, we're now going to have this conclusion. For instance, if I'm working with the unbiased estimator, I told you the other time, the variance and the mean square error, they're going to be the same. But if I'm working with the biased estimator, if an estimator is biased, then we expect the variance to be greater than we expect the mean square error to be greater than the variance. And that is the reason why, if I want to compare a biased estimator with any other estimator, I will need to use the mean square error of the bias estimator, not the variance. Because the mean square error of the bias estimator will always going to be greater than the variance of the estimator. Is there any question before moving on? Is there any question? Any question? Okay, you're good, right? Now, we now want to move. Please, I want to move into this example right now. Okay, if you don't understand, you pay for the service. You deserve to be served better. Do not hide your feelings. Okay, ask me question. Now we want to go into another. I want to go into this example now. We have y1 up to yn that are distributed identically and they are independent. They follow uniform distribution. Now, we take a look at this guy now. That's a uniform distribution, right? The uniform distribution has two parameters. Okay? The uniform distribution has two parameters, and the uniform distribution actually have what I call a lower bound and the upper bound. But right now, the lower bound is known to be 0, but the upper bound is unknown. That is what you see as theta. Now, the parameter that is unknown needs to be estimated. Okay? Now, this is the distribution. The f of y equal 1 over theta. Don't forget what you've done before is 1 over b minus a, right? 1 over theta minus 0. That's going to be 1 over theta. That's why you have the density function, okay, to be, give me 1 second, to be 1 over theta. And of course, the mean and the variance, make sure you revisit the mean and variance of a distribution, okay? The mean, I remember for uniform, is b plus a over 2. So this is going to be theta plus 0 over 2. That's why you have theta over 2. And the variance is, I think the variance is b minus a all squared over 12. Okay, that was why you say theta squared over 12. Okay, and you know what? The CDF is also known. And what you can see is the density curve. Okay, I call the density plot. Okay, and as well as the accumulative density plot. Now, where are we going? Do you know that if I want to figure out the expectation of random variable y as well as the variance of random variable y, they are all depends on the values of the parameter theta. If I don't know theta, there's no moving forward. Go ahead. Or are you talking about this one? Yeah, you know, uh, the a random variable y for uniform, the lower bound is 0 as indicated. The upper bound is theta. So that's why you see that. Oh, okay. The idea of the hairs. Oh, that's a good question. You know, when you're doing CDF, for instance, maybe I'm working on an uppercase f of y. You know, I'm going to integrate f of y, but I'm not going to say lowercase f of y. I'm going to say lowercase maybe f of t or something else, the t, because this is going to go from 0 to y. So I'm going to change the other one. So it doesn't matter what you see here. Okay? Okay, now I want to move right now. Okay, so I want to move right now. Now we're given that. What do we want to do? Okay, please, I need you to pay attention. I spend a lot of time explaining. I don't want to, but I wanted to get the information on a normal ground. I know this is complicated, but I want to believe when you take your time, okay, and you are able to understand the reason why we're doing what we're doing, you're actually going to appreciate what you're doing mathematically. Now, what do we say we're looking for? We're looking for theta, right? Whenever we're looking for theta, then we need to go to the population. Which population? The population whose probability distribution is uniform, right? And we're going to take a sample. Now, when we take a sample, what are we going to do? With a sample, we want to estimate theta, unknown parameter theta. Then we need estimator. Okay, we need estimator. Take a look at this guy. These two estimators were suggested because there could be more than one estimator. Estimator is a method. Don't forget, it's a method that we use, okay, to actually to have a numerical summary of the sample. Okay, now the first estimator suggests, oh, if you want to find the unknown parameter, all what you just need to do, find the mean of the random variable, then multiply by 2. That is why you see 2y bar. Okay, now the second estimator say, okay, you know what? Just get the maximum of the random variable. Does that make sense? Of course, in 4101, you've done what we call order statistics. Okay? You've done other statistics. So this guy is trying to tell you this, the second estimator suggests, okay, get the random variable y1 up to yn, they're the maximum of them. Okay, we represent the theta. Now, these are estimators. We got two estimators. Now, what are we going to do to know which estimator is better? We need to investigate the property of an estimator. What are the property of an estimator? Number one, we're going to investigate whether they are biased or they are unbiased. Now, if an estimator is unbiased, then I need to obtain the variance of an estimator. If an estimator is biased, then I need to obtain the mean square error. Does that make sense? That's what we want to do. Okay, now take a look at this. What am I doing here? I need you to be focused. Okay, I need you to just take a look at that. I want to find, if I want to investigate whether an estimator is unbiased or biased, I want to start with the first estimator. I'm going to do expected value of theta cap 1. And what is theta cap 1 is 2y bar, right? And don't forget, oh my God, take a look at this guy. We know from theory, we know from what we've done before, expectation of y bar is the expected value of y. And what is the expected value of y? You already been given to be theta over 2 initially. You saw what I projected earlier in the previous slide, where they give you a random variable y. You need to be able to know what is the expected value of y. What is the variance of y? Now, the expected value of y bar is the same thing as expected value of y. When I plug that in, what does it give me? That give me theta. Oh my God. When the expected value of an estimator give a parameter theta, that estimator is unbiased. Any question? Now, this is to show that theta cap 1 is unbiased because of the fact that the difference between this guy and theta is 0. Because theta, that guy give us theta, so theta minus theta will be 0. And that is why, that's what I'm trying to say here. Now, we have investigated the nature of the biasedness of theta cap 1, and we've come to a conclusion that theta cap 1 is an unbiased estimator. The very point of call, if you want to investigate how good is an estimator, you need to start your journey by investigating the unbiasedness property first. Now, and I want to do the same now to the other. Now that I've done that, because it is unbiased, that will now tell me I need to get the variance. If it is biased, I need more than variance. I need a mean square error. Okay. Now, right now, I want to get the variance. Variance of what? The variance of theta cap 1. What is theta cap 1? It's 2y bar. Don't forget 2. When 2 is coming out, it's going to be 2 square, right? That will be 4. Variance of y bar. Oh my God. You remember what you've done before. The variance of y bar is the variance of y divided by n. Don't forget. That applies to all distributions. Now, you've been given the variance of y in the question. The variance of y was theta squared over 12. You remember? This guy was theta squared over 12. Okay. Now, if I apply that here, that would be theta. You're actually going to have theta squared over. You're going to have theta squared over 12n. And don't forget, what about the 4 that is outside? By the time you simplify this guy, okay, 4 goes there, then you're actually going to have theta squared divided by 3n. Any question? That is the variance of theta cap 1. Okay, theta squared divided by 3n. Okay, now I want to move right now. Now, if I ask you to find the mean square error of unbiased estimator, I'm just wasting your time. Take a look at that. Because for the unbiased estimator, the mean square error is going to be the same as the variance. Okay, that's just wasting your time because the bias is going to be zero. You're still going to have that. Does that make sense? Because I can decide to play on, professors have a lot of trick. Okay, so if I were you, if an estimator is unbiased, and I asked you to find the mean square error, all what I just need you to tell me is the mean square error is also going to be the same as the variance. Okay, now we have investigated the first estimator. We want to go into the second estimator. Now, the second estimator is complicated, and I will need you to actually be focused. In statistics, there's something that we call order statistic. You did that in 4101. Now we want to talk about, the second estimator is maximum order. What is it? Maximum order. Can somebody tell me in practical term, what is the real life application of maximum order statistics? Where do you think we can apply that in practical term for extra credit? Can somebody tell me? What is the real life? You've done order statistics before in 4101. Yeah, what is the real life? You see what? Yeah, that's kind of close. You are right. That's kind of close. Thank you for that. Now, do you know the idea of order statistics was used in the Second World War? I'm going to give you an example now. Some weapons of the Nazis were captured during the second, and on weapon they write serial number, right? Now let's say those who are fighting the Nazis, they really want to know how many weapons do they have in their arsenal. Okay, they want to figure out the numbers of weapons in their arsenal. Why can't they send a spy? Why can't they send somebody who can spy? Because somebody who can spy can give a wrong information. And that is why we normally trust statistician than somebody who spy. Now, this is what is going to happen. Let's say they capture some guns, some weapons, 5, with serial number 5, 13, 721, and let's say 21. Let's say they capture these 4. Okay, they capture these 4, and we want to figure out, because by serial number, we want to figure out what is the last serial number. What is the last serial number in our sample? 720. The maximum in our sample is 721, right? The minimum in our sample is 5, right? 720, the 721 in our sample is telling us if we should take another sample of their weapons, 721 is not going to be the maximum. Therefore, the maximum become a random variable. Then we need a probability distribution for maximum. What do we want to use the probability distribution to do? We want to find what is the probability that what they have what the maximum is going to be 1,000. That's why you do other statistics. Okay, and that is also very useful in quality control. Now, whenever you want to talk about maximum, maximum is talking about the maximum number, after arranging the values in ascending order, then you need to first start by finding what is the probability of the estimator less or equal to S. Is that not CDF? That is a CDF. Okay. Now, what is it? What is the theta cap 2? The theta cap 2 is the maximum order statistic that they talk about. Where am I starting from? I'm actually starting from what is the probability of the theta cap 2 less or equal to S? I'm actually going to start from CDF. Now, after that, then maximum, then I'm actually going to split. It's going to give you opportunity to split. What is the probability of y1 less or equal to s, comma, y2 less or equal to x, until I get a yn less or equal to x? Take a look at that. Oh my God. Because they are independent, okay, and they are identically distributed, I can actually, without wasting my time, I can just go to this. I can just write one, just one, and raise it to the number of the sample size because they are identically and independently distributed. That was why I can actually do that. So the probability of y less or equal to x raised to power n. And you asked a question the other time. We already know the CDF of the distribution. Okay. What is the CDF of the distribution? Okay. The CDF of the distribution was S over theta. Now, but the CDF of the old, here you actually having the CDF raised to power the sample size. Then that's why you're going to have this guy here. Okay. S over theta, all raised to power n, assuming that same CDF for every random variable. That's what we mean. Okay. Now, when you get a CDF of this is the CDF that we are talking about, the CDF of the maximum order. Then I can find the PDF from the CDF. There's a relationship between a CDF and a PDF. Okay, so when I have a CDF and I want to get a PDF, then I'm going to do derivative. I'm going to do derivative of that. Okay, now that is what you see here. You see, I want to get the F. The PDF is a lowercase f from the CDF is an uppercase f. What I derive, then I'm actually going to perform a derivative on that. When I perform derivative, I'm actually going to have this guy here. Now, this guy, that is what we want to use. That is the probability distribution of the maximum order statistic. What do I want to achieve with the probability distribution of the maximum order? Oh, I can find the mean. I can find the variance. Does that make sense? Because I know the distribution now, and that is what I want to do here. Take a look at this guy. What am I doing? I want to find the expectation of theta cap 2 because I know the probability distribution of theta cap 2. So it's just going to be S. Then the distribution that I got. Then so here now, I'm actually going to perform an antiderivative. And at the end of the day, I'm using the range of, don't forget, 0 to theta. They gave you that initially. And at the end of the day, what do you have? What is the final result? The final result is n over n plus 1 theta. Does that give us theta? That gives us something other than theta. It means theta cap 2 is unbiased. Is biased. Can you see that now? The theta cap 2 is biased because if you take a look at that, and if I want to find the biasedness, okay, how am I going to know the biasedness? You're just going to come here. Take a look at this guy. That's how to find the bias. What do we have for the expected value of theta cap 2 is n over n plus 1 theta, then minus theta. By the time you simplify that, this is the bias. Does that make sense? That is how we got the bias. Any question on how we got the bias? Go ahead. Go ahead. Okay, this is how I got it. You know this guy? Is what I got for that guy, right? Then I'm gonna plug that here. So which is gonna be n over n plus 1 theta minus theta. Then I'm gonna say over 1, simplify. SCL is gonna be n plus 1 up there. N plus 1 goes, it's gonna be n theta minus, okay? So that's gonna be n plus 1 into theta. Okay, when you simplify that, n theta minus n theta minus 1 divided by n plus 1. Okay, this cancels that. So that was how you actually go that. Oh, sorry, that's a theta here because the theta here, n plus 1 multiply going to be n theta plus theta by the time you expand. So that is an algebra. You see that? We got the bias to be that. That is the bias. Okay? You need the bias in case you're going to find the mean square error. Okay? So take a look at that now. Now, what have we seen here? We've seen that the theta cap 1 is unbiased and theta cap 2 is biased. And we've obtained the, but let me tell you this. Do you know, what if I ask you a question, even though I know that this guy is biased, if I go by the law of large number, where I work with a sufficiently large sample size, is there a possibility that this guy is going to go to zero? When bias go to zero, that is unbiased. Now, because the sample size is in the denominator, when the sample size is large, that guy is going to tend to what? Zero. Now, in this situation, we call it asymptotic unbiased, which means initially it was biased, but when the sample size is sufficiently large, it's actually going to be unbiased. But we're still going to call it bias for now, because it is not an unbiased estimator for all sample size. It's only unbiased when sample size is sufficiently large. Does that make sense? Okay, now what are we going to do next? What we want to do next to this estimator, we need to compute the variance. After that, the combination of the variance and the bias will give us the mean square error. Now, let's move it forward now. Now, you see what we're doing here? You've done this before in 4101. If I want to find the variance of an estimator, it's expected value of the estimator squared minus the expected value of the estimator, everything all squared. Okay, so what you're doing here, what you're doing in the integral now, you raise s to the squared, because you want to find the expectation of that squared. Okay, minus the square of what you got, n over n plus 1 theta was what you got as the expectation of the theta cap before. And at the end of the day, let's see the variance. You need to be able to simplify, okay? You need to be able to simplify, okay? When you simplify, this is all you got. This is the variance expression. The variance also depends on the sample size, okay? Take a look at that. Now, because the theta cap 2 is biased, okay, if I want to evaluate the performance of theta cap 2, I'm not going to use the variance. I'm actually going to use the combination of the variance and the bias that we call mean square error. So let's proceed now to the mean square error. Oh my God. We are now using take a look at this. We want to find the mean square error of theta cap 2 now using what we derived the other time. The mean square error of an estimator can be equal to the variance of an estimator plus the square of the bias. Let me tell you this. If your variance expression is wrong, your mean square error will be wrong. If your bias expression is wrong, the mean square error will be wrong. That's why you need to be careful, okay? So take a look at that. I'm plugging that in now, and that actually give me this guy. Now, I've been able to obtain the mean square error for the two estimator. Now, if I want to go by whether one is if I want to use the principle of unbiasedness, I already know that the first estimator is unbiased, but the second estimator is biased. But let me tell you this, even though we want unbiased estimator, okay, and in most of the realistic situation, we may not be able to get unbiased estimator. Now, how can we actually compare the performance of biased estimator and the unbiased estimator? Now, I need you to listen now. If I want to compare two estimator and they are unbiased, I'm actually going to use the ratio of their variances. Why am I using variance? Because they are unbiased estimator. And why am I using variance in the first place? Because variance measures efficiency. When an estimator have a minimum variance, it means that estimator is more efficient. But right now, because I'm actually comparing a biased estimator with an unbiased estimator, I'm only going to compare the ratio of the mean square error. Does that make sense? And of course, the mean square error of the unbiased is the same thing as the variance. Okay. Now, That is exactly what I'm doing here. Take a look at this guy. Theta square over 3n is what we got before as the mean square error, also the same as the variance of theta cap 1, that is unbiased. And this guy is what we just get right now. Then we simplify. After simplifying, we got this guy. We got 6n divided by n plus 1 and n plus 2. Okay. Before I explain asymptotic behavior of this ratio, I will want to say this. We want to compare. Which one do you have in the denominator? Right? If the ratio give 1, if I'm comparing and I'm using ratio, if ratio give 1, it means they are equally efficient. Does that make sense? If the ratio give 1. But if I really want to test here, if I want to test which estimator is better, let's first start with the sample size 1. Can we start? With the sample size 1, if you plug in 1 to where you have n, they will be the same. That will give you 1, right? Plug in 1. 6 times 1, 6. If you plug in 1 here, 2. Plug in 1, 2 times 3, 6. The ratio is going to give 1. At sample size 1, the two estimators are the same. But let's look at what happened from 2. From sample size 2. 6 into 2. Okay, 2 plus 1. That will be 6 into 2. That will be 3. Okay, 4. They're still going to be the same. At sample size 1 and sample size 2, the two are the same. Now, let's look at sample size 3. Okay? Sample size 3, 6, 3, divided by 3 plus 1, 4. 3 plus 2, 5. 18 over 20. Hello? Can you see that? 18 over 20 from sample size 3 and above. Okay? Now, the 18 over 20 means less than 1. Right? When a ratio is less than 1, it means the denominator has a bigger one. That's why the ratio is less than 1. And don't forget, we're looking for estimator with a smaller variance or smaller mean square error. And that is the reason why I made this statement. Theta cap 2 is asymptotically better than better estimator than theta cap 1. Why do I use asymptotically? It means for large sample size, at least from 3. Does that make sense? Any question now on this? Any question? Go ahead. Yeah, you're always going to start from 1. You know, because you may not be able to tell uh because this is independent. But if you don't want to do that, let's say you don't want to say n equal to 1, n equal to 2, then we're going to borrow from limit theorem in mathematics. In the limit theorem, as n tends to infinity, this guy is going to tend to 0. Go ahead. Because the way it is, it will be difficult to tell which one is smaller. Because look at the expression. I understand what you mean. Let's say, for instance, you get a value that you can see. You'll be able to know this mean square error is smaller than this. Oh, this is better. But right now, there's no way to tell until you simplify, until you test for the sample size. Does that make sense? And we believe that when the ratio is less than 1, when the ratio is less than 1, the one at the bottom is the bigger one. When the ratio is greater than 1, when the ratio is greater than 1, the one at the top is the bigger one. But which one do we want? We want the small one that give us the smaller one. That is the one that will be more efficient. Does that make sense? Okay, now I want to move right now. That one is not really, that's just talking. Now, this guy is just talking about the distribution. The theta cap 1, is looking, the distribution is looking normal, but for theta cap 2 is not. But it is not about normality. Does that make sense? But it's about convergence. It's about like can we trust a model? Do you understand? Even though normality is good. Why do we want normality for? For easy computation, okay? Of if you want to answer a probability question around a random variable. Now I want to introduce us to common estimator, unbiased estimator. I think I'm also going to, when I'm not able to finish this, then I'm going to, actually combine it with what I'm going to teach next. But take a look at this. These are common. Now, what we use in statistical analysis most, take a look at this. Those are parameter, mu, mean, population mean, proportion, difference of that. Now, if I want to investigate them, I'm going to take a sample, right? And what would be the estimator? These are the estimators. And let me tell you this, these estimators, they are unbiased. Why? Expected value, we've proved that. Expected value of y bar is mu. Expected value of p cap is p. Expected value of p cap 1 minus p cap 2 is p1 minus p2. Okay, expected value of y bar 1 minus y bar 2 is mu1 minus mu2. This have already been proved statistically. Okay, take a look at that. Now, this is the true parameter. Now, because of that, because they are all unbiased estimator, we're only going to be focusing on their variances. Now, what you see here, they are the standard error, which is the square root of their variances. If you take a look at the first one, what is the variance of y bar? Sigma square over n. What is the square root? Sigma over root n. That's what you see. If you take a look at the second one, do you remember? Do you remember for Bernoulli? P into 1 minus P for Y variance. For Y bar, that find the square root. See that? 1 minus P is what we call Q. That's why you see PQ over there. Then for the difference of mean, for difference of proportions, I want to believe when you do lower level course in statistics, you've done test of means, t-test of means, and test of proportions. Okay, the estimator use are unbiased. Okay, and that's why we focus on the variances. Okay, lastly, I'm going to talk about this lastly today. I'm going to talk about this lastly. I think I just talked about all of this. Okay, but y is a random variable. The estimator is y bar, which is what we call the sample mean. Okay, and if we're dealing with proportion, we are y1 up to yn is Bernoulli. Expected value of y, a particular y is p, the variance is p into 1 minus p. Then when I'm dealing with the sum, which is going to be binomial, then the mean, p cap is the same thing as y bar. I told you the other time. Okay, now expected value of p cap is the same thing as expected value of y. And of course, the same thing applicable to the variance. If you look at now, what am I? Oh my God, what am I doing here? What am I doing here? Take a look at this guy, right? Expected value of p cap is the same thing as expected value of y, which is the same thing as p. We're using the that comes from Bernoulli distribution. Now, what is the variance? The variance of y for Bernoulli is p into 1 minus p. But what is the variance of p cap? P cap is the same thing as y bar, which is variance of y over n. So p into 1 minus p over n. Okay? And because p cap is unbiased, let me tell you this. If y bar is unbiased, p cap will be unbiased because p cap equal to y bar. Therefore, the bias of p cap will be 0. When the bias of p cap equal to 0, then the variance of p cap and the mean square error of p cap, they're going to be the same. What is this guy asking me? Distribution of p cap. The first one, the mean is going to be p. Okay? The mean, the variance is going to be just that guy. 1 over p, or p into 1 minus p over n. I'm actually going to stop here. I don't want to rush you. In my next lecture, I'm going to start from slide 14. Okay, we have 6 more slides. Is there any question before I go today? Now, before I go, I quickly have this announcement. We are getting into complicated situation now. If you know you are stuck in this class, please write me, send me a message. Okay? Meet with me during office hour. It is expected that it could be getting tough mathematically or statistically. That is expected. Do not hide your feelings. Okay? Whatever you discuss with me will be treated with absolute degree of confidentiality. I can assure you that. Okay, make sure you all stay safe and have a lovely day. Bye for now, everyone.